Hey. Okay, slightly less clear. Maybe one more. Okay, Charles and Rachel, and any questions, homeworks? We think it will be a bit fuzzy. Trying to see how hard is my computer working. Okay. Seems that it's maybe it's sharp enough. Questions, bureaucracy, anything? I didn't decide about what will be the formality of the exam. As usual, it will not be 24 hours window. It will be one time for the exam. What might be that I'll have actually 2 windows, and every person can, as far as they care, go to the first time, to the first final, get her or his results, decide that he doesn't like this result, and then go to the second time. That probably will be a week or so later. Or if you cannot go to the first one, just go to the second one, something like this. But the only caveat is that if you're going for the makeup part, then it will replace your grade, no matter. I'll also put it on a post about it. When I mentioned all the things about class participation and that it can change your grade, one of the things that plays big role in my book is, did you submitted all 6 homework or only 5? I strongly recommend to submit homework 6 no matter what. Even if you didn't succeed to solve all the questions, even if you have 5 homeworks that you are okay with them, well, you don't have to, the formula is that I'm ignoring the lowest grade. But even if your grades are, say, even if in homework 6, you got exactly the same grade that you got in the first 5 homeworks, even if your grade in homework 6 is the same one that you got in your first 5 homeworks, it still plays a big part in my books that you really cared about trying to improve your homework grade, and was putting the time and effort to submit all homeworks. So I strongly suggest both as preparation for the midterm, for the final, and both as to show more class participation, to submit all 6. Okay, assuming there is no bureaucracy questions, we are talking about a suffix trees. Remember, there is no such thing as suffix twice. There are suffix trees and there are tries. And I want to use some theory when I'll talk about the efficiency and the complexity of the tries of the suffix tree. I will need a bit theory. So let me play with some theory. Here is a tree. This, as you know, is a tree, or to be more precise, I'll think about it as a rooted tree. What is the difference between just a tree versus a rooted tree? Rooted tree is any graph that is connected, doesn't have cycles. To make the tree a rooted tree, I picked one of the vertices. I decided that this is a root, call it root, and then I'm using gravity, like let the other vertices pull down, so it's clear relationship of who is a parent of whom. Right? Otherwise, I don't know. I cannot speak about, without a root, I cannot speak about parent-child relationship. So that's a tree. It might be a binary tree, maybe not. Maybe some nodes have only one child, maybe have two. Think about trees, and I'll say that this tree is, my terminology, is the tree is family, and am I still in, I'm in the other camera, so it will. The tree is family blessed or children blessed. Or for short, we'll just call this tree blessed. That's a definition. If each internal node has at least two children. So what are internal nodes? Let's first understand. That's a leaf. A leaf is a node with no children. Kind of obvious. And every node that is not a leaf is an internal node. The root is probably an internal node, unless your whole tree is just a single root, and then there is no internal node. It's just one leaf. But that's really the only case. So we have a few leaves in this tree, namely 1, 2, 3, 4, 5, 6. And Zoom people, is this tree blessed? Blessed means everybody that is not a leaf has at least two children. Somebody? What? Anybody? Is this tree blessed? Is every internal node has at least two children? And the answer is no, because of this node V. V over here has only a single child, the green one. So, but if now I add another guy over here, then this tree is finally blessed. Every node has at least two children, some has 3, maybe some has many, many more. And, oh yeah, oh, by the way, all the trees that I'll discuss will be rooted trees. How far can I go? All the way to here. Oh, now I need a few notations. N will be the total number of nodes. L will be the number of leaves. And I will be the number of internal nodes. obviously L plus I give us the total number of nodes. Some are leaves, some are internal nodes. Hello. Since you were late, I mentioned at the beginning that I'm debating about good chances we'll have two windows, and you can go. I'll do what universities in Israel are usually doing, which is you can go to the first test, first final, decide that you don't like your grade, and then go to the second one that will be about 4, 5, 6 days later, and takes a second one, or just takes a second one, or just takes a first, of course. But if you are taking the second one, it will override your grade from the first.
That's for the final.
Yeah. Everybody's to mention what I was talking about, I need something from theory, which is trees is any connected graph which doesn't have cycles. My trees will have a root, which means that now every node has a parent and several children, maybe 0, maybe few. Leaves are the nodes that have no children. Internal node is any node that has at least one child. Okay, and I just gave a few quantities that I'm going to use, which is L is the total number of nodes, L will be the number of leaves in my tree, and I will be the number of internal nodes. Now, if my tree is not blessed, in a tree that is not blessed, could it be that L in a non-blessed tree could it be that L is smaller than I? Zoom people, is my fonts readable with at least one of the cameras? Amir?
It's average.
It's a little bit blurry, but I asked Amir and he was like reading it for me, so it's all good.
Okay, I'll use it a bit. Is the computer makes it fuzzy? I think that the up camera has a crappier resolution. So
yeah, well, one of the cameras is pretty good. The two on the right are a little bit fuzzy.
Which one? Where I am right now, right? The camera at the top of the room.
Yeah, that one's pretty good.
So which of the 3 cameras are fuzzy? This one, or this one where I'm here, or this one where I'm here? Or
like the top
the
right.
second one?
the top one.
No, the top right on the overleaf.
The top right, the one that I'm blocking now, that's a fuzzy one?
Yeah, that one.
Okay, in this case, at least partially solved it. Yeah, I keep forgetting to bring glue. And we have plenty of other cameras, but at least partially. It's maybe solved. Will be better. Another camera. So, people question, could it be that L is smaller than I in a tree that is not necessarily leaf? That is that it has fewer leaves than the number of internal nodes. The number of internal nodes is larger than the number of leaves. In general, binary something tree. Example?
Just have one child.
I'll make a node that has one child. This example will not work because I have one internal node, namely the root, and I have one child. So here the numbers are the same. Here numbers are the same. There is one internal node and one leaf. One more node. So now I have two internal nodes, but only one leaf. So in a general tree, binary or not, I cannot say anything about the relationship between them. Maybe I have more nodes and more internal, maybe I have more leaves. On the other extreme, of course, will be this tree. This tree, lots of leaves, one internal node. But let's talk now about, so without the assumption about being blessed, I cannot assume much. I cannot say anything about relationship between number of internal versus number of leaves, number of internal versus number of leaves. But let's assume that from now on, my tree is blessed, then lemma in every blessed tree, my definition blessed tree, normally it's just called two regular trees. In every blessed tree, the number of internal nodes is smaller or equal than the number of leaves minus 1. In every blessed tree, the number of internal nodes is smaller or equal than the number of leaves minus 1. Proof by example, let's just draw all possible blessed trees. Proof by example, here is one nice tree. But in this tree, n, by the way, is 3, the total number of nodes. L is 2 leaves, and I is 1, only one internal node, which is a root. Yet another example. In this great tree, how many internal nodes do I have? For my internal nodes, this and this. Who are my leaves? Everybody else. 3 leaves, only 2 internal nodes. So I win again. And this is a blessed tree, right? Every node either have at least 2 children or no children at all, and then it's a leaf. Of course, let's take this tree, let's add another leaf over here, then this lemma still holds. L is even larger. If it shows 2 before, then it's too large. So I proved it for at least a few trees. Let's now prove it for arbitrary trees. So proof by induction on n, which is the total on n, which is by induction on the number of nodes, that is n. How does induction works? We need to prove something about that the lemma holds when n, the total number of nodes, is very small, which actually I just did. I covered all the trees with 2 nodes. I covered all the trees with 3 nodes. Who are the blessed trees? The blessed trees with 3 nodes? Only this guy. But everybody agrees this is not a blessed tree because this internal node has only 1 child. So not this guy. So I just proved the case of n equals 3. And now, how does induction works? I assume that this lemma, the lemma that every blessed tree has, the number of internal nodes is smaller than the number of leaves minus 1, assumes the lemma is correct for all trees all blessed trees. With less than n nodes. I checked every tree, I think about n that is 17. I checked every tree that has 16, 15, 14, 13, etc. Every tree that has less than 17 nodes, I checked and it works. N equal 4, say trees with total number of nodes is 4. I checked every tree with 3 nodes, which is only this guy, and the lemma is correct for this tree. Now I want to prove that it's correct also for trees with 4 nodes. And once I prove that it's correct for trees with 4 nodes, I'll switch and talk about trees with 5 nodes. And if I prove it for them, I'll prove it for 6 nodes and so on. So in general, I want to show if it's true for any tree with less than n nodes, then it's also correct for tree with n nodes. Okay, let's continue here. So assume that the lemma is correct and let T be a blessed tree with n nodes. I assume that everybody has seen at least one case of induction, and if not, then you'll see another one now. If I had a tree that looked like a linked list, yeah. So I don't know where you, yeah. Okay. That's this case. So let tree be a tree with n nodes. Let V be a leaf, and let W be parent of it. So now my tree looks like all blessed, yada yada yada. Let's take one of these nodes and make it V. There is one of these nodes, I'll call it V. I just change the size for font reasons, and and I'll change the size for font reasons, and I'll also say and assume furthermore that V is as far from the root as possible. V is as far from the root as possible, so actually this is not the V that I wanted, because the distance of this node, V the leaf, the distance from the root to this guy is 1, 2, while I can pick another leaf, this guy, whose distance from the root is larger. 1, 2, 3. 3 edges toward this guy. I'll just zoom in into this guy. So here is V and here is W. And the whole tree has n nodes. And what I'm going to do now is erase delete V. And now there are two cases. two cases, namely W or the T is still blessed. That is, the parent of the parent WV still has at least two children, and the other case would be, of course, that T will stop being blessed. The other case is that now W has only one child. And I want to convince, however, after deleting V, my tree doesn't have n nodes anymore. My new tree has n minus 1 nodes. To repeat, lemma, number of internal nodes is smaller than the number of leaf minus 1. That's what we're trying to prove. So we have two cases. In the case of in case 1, the new tree has n minus 1 nodes because I just deleted the leaf, and is still blessed. It's still a blessed tree. That would be the case right here. But W has 4 children. If I delete V, then the tree after deleting V is still blessed. But now it has n minus 1 many nodes. So it's still blessed. It has n minus 1 many nodes, which means that the currently number of, I can imply the induction hypothesis. What did I prove with the induction? For every tree that has less than n nodes, this lemma holds, provided that the tree is blessed. So in the new tree, I is smaller than n minus 1, which is a number of nodes in the new tree. Sorry, what happens to the number of leaves in my new tree? What can I say about the number of leaves that happens because I deleted W? I deleted W, I deleted V, but its parent W still have many children. So what the new L prime, new L number of leaves is the old number of leaves minus 1. I didn't change the number of leaves, and nobody became internal. Nobody became a leaf. So right now I can apply the new lemma. The number of internal nodes in the old tree and the new tree are the same. So the number of internal nodes is smaller than the current number of leaf, which is L minus 1 minus 1. That's what the lemma says about every tree that has L minus 1 nodes. But if this is true, then it definitely true that I is smaller than L minus 1. Right? If I is smaller than L minus 2, then definitely I is smaller than L minus 1. It's larger number. But I mean, maybe I was able to confuse you, but it's just the more I talk about it, it's more confusing. If in the old, if when I deleted V, the number of internal nodes didn't change, the number of leaves was decreased by 1. I have a tree with n minus 1 nodes, and in this tree I apply the induction hypothesis. For example, when n was 4, now I got back to the case of a tree with only 3 nodes, and for tree with 3 nodes we already proved it. Correct? So in this way I can prove that the lemma is correct for every tree with 4 nodes, when n is 4. When I'm done when proving the correctness for n equals 4, I move to n equals 5, n equals 6, and if I start with n with 6 nodes, then by deleting a node, I'm in a tree with 5 nodes, which is the case that I already proved. That's how induction works. When I'm done with this, I'll show to you that all the students at our university, special university, all of our students at the university all have the same height, by the way. It's a kind of important fact. So the first case that is easier, I just convinced you, hopefully. So the first case assumes that W, the parent of V, remember, V was here, and I just deleted it, another child of W. The first case assumes that W still have at least two children after after V was deleted. But now assume that I deleted V. Assume that assume that W has only one child in the original tree. W has 2 children in the original tree. It was a blessed tree, it was perfect. However, V was here, and I just deleted V. I just deleted V. But now I'm in trouble. If W right now has only one child, I'll call this other child U. And in this case, I will delete U as well. Why? Because for if I just deleted V, what I'm getting is not a blessed tree. A tree that is not blessed, I cannot argue anything. I don't have any claims about a tree that is not blessed. This lemma I want to convince you only for blessed tree. So I deleted V, realized that V has only one sibling, only one brother or sister. So I deleted U as well. How many leaves? What happened to the number of leaves? What is if L was the number of leaves in T, and L prime is number of leaves in the new tree. Obviously, in the new tree, well, it's not obvious, but what's the relationship between which one is larger and what is the difference between the number? L? What's the relationship between L and L prime? L prime is what happened to the tree in the example over there after I deleted V and W as well. Sorry, after I deleted V and the only sibling of the V. It is L prime is a number of leaves in the tree after I deleted U and after I deleted V. True or false, L prime, the number of leaves now, equals L minus 2. Because I deleted 2 nodes. And other very scared or very incoherent. Correct? Incorrect? I deleted 2 leaves. So the number of new leaves equals the number of leaves before I deleted anybody minus the 2 that I just deleted. Anybody? Zoom? Help? I deleted V, I deleted U, that is I deleted 2 leaves. How many leaves do I have in my new tree? Minus 1, thank you. L prime equals L minus why is this 2? Somebody else. Why is this 2 that L prime equal L minus 1? I just deleted 2 leaves.
Because after you delete 2 lists, you also create another.
What happened to W? It was internal, but we said we are in the case that W has exactly 2 children. I just deleted these 2 children, so W became a new leaf. So I deleted 2 leaves and added 1 new leaf, or 1 internal node became a new leaf. So L prime is L minus 1. And I prime, the number of internal nodes. Internal nodes meaning node with only 1 child. Sorry, internal nodes are nodes that are not leaves. Correction. I prime is the number of internal nodes in the new tree. That is after I perform these 2 deletions. What is the relationship between I, the number of internals in the old tree, versus I prime? I versus I prime, number of internal nodes.
-1.
I prime equals I, the number of internal nodes in the old tree, minus 1 because W just moved to the other thing. W used to be an internal node and now W became a leaf. Okay, and my new tree is of course blessed. But if in my new tree, the number of nodes in the new tree n prime equals n minus 2, of course. It was a previous number minus 2 nodes that I just deleted. And don't care about the exact number, but this number is smaller than n. And minus 2 is smaller than n, meaning that I can use the induction hypothesis. induction hypothesis says for every tree that has fewer than n nodes, the induction hypothesis holds. What is induction hypothesis? What are the lemma? The lemma is correct for every smaller tree. For example, I started from a tree that looks like this. This will be a good example. Started from a tree that looks like this. This is U, this is V, this is W. I deleted U and V. W became a parent, and now I'm in the case of a tree with only 3 nodes, as an example. In general, in my new tree, n prime is smaller than n, so I know that the induction hypothesis is true. So the I prime, number of internal nodes in the new tree, is smaller than L prime, number of leaves in the internal tree, minus 1. That's, I know, because I proved it for any smaller trees. What do I need to prove? That the new I is smaller than the new L, sorry, that the old I, before the deletion, is smaller than the old L minus 1. But what really do you say? What is the relationship between I prime and I, number of nodes that we started with, is I prime plus 1. I just move the 1 to the other place. L is just L prime plus 1. We just establish it. So if this is true, then it's also true that from this it follows that I is smaller than L minus 1, number of internal and number of leaves in the new node, in the original tree, before reduction. So now we proved it from every tree with 3 nodes to every tree with 4 or 5 nodes. And from 4 or 5, we can prove it to every tree with 6 nodes, and from using exactly the same argument from every 6 to every 7, and so on till infinity. Oh, and how many of you know played with inductions before? Saw induction in any stage? You've done, you guys have not. People on Zoom? No, never mind. For the sake of time, we'll. This is little. Okay. Quick induction hypothesis. Every set of n students all have the same height. Every set of n students all have the same height. This is a fact of life. Had you ever thought differently, it's only optical illusion. Let's prove this claim. Let's n be, let's work on the case of n equal 1. In every set of 1 student, S will be a set that contains exactly 1 student. Is this claim true for a set of 1 student? Are all the students in this set have the same height as every other student in this set? Is every student in this set has exactly the same height as every other student in this set? Yeah, they all have the same height because it's just 1 student. So the base case, check. Now let's continue by induction. Take a set of n students. Here's one of them, x. I'll take this set and I'll generate a new set. I started from a set S, and now I generated a new set S prime, and S prime has n minus 1 students. in the word set. There are n minus 1 students, and they all have the same height. By the induction hypothesis, we proved our induction hypothesis for every set with less than n students. Let's think about one of the students, y, over here. One student, y, over here. Y has the same height as every other student in the wedge set. Let's generate a new set. I want to generate a new set, S double prime, and my new set will be, I'll pick one student that doesn't appear anywhere here. Let's call him or her Z. And Z, and my new set will be S prime, and I take S prime and I add Z into this set. This is my new set, S double prime. So S double prime is just S prime union with this new guy, Z. Z has a so S double prime has only n students, so they all have the same height. In particular, Z and Y have the same height. Now let's generate our last set, which will be everybody else together. Everybody else together. What did I prove? Z has the same Y as Y, but Y has the same height as X. Z has the same height as Y, and Y has the same height of X. In particular, Z and X have the same height, which is a common height for everybody else. And how many students do I have in my very new set? It's n plus 1. So if my proof was correct for any set with n students, and it's true also for any set with n plus 1 students. And you were living with a total illusion all your life. So yeah, it's actually a good exercise in induction to think about this case. And we are back to we are back to a suffix trees. So I hope everybody remembers what are tries and what are suffix trees. Suffix trees, I take a book and I look at all the suffixes of this book, and every suffix of the book will be a word that I'm going to insert into the try. And basically, I'll say every word that I'm looking for in the book will be a prefix of a suffix of a word in the book. I want to remind everybody the compression idea, path compression. If you have a long list of nodes, each one has only one child in the try. In the try in general, you can say, hey, this string of words represent, this collection of words, only this part, represents some strings in the alphabet. Right? It will be in this case B, followed by B, followed by B, yeah, and a node that has two children, So I'll store the B as a string in this case. Just compress it, so I don't have to waste so much empty space. Okay, suffix tree, quick reminder, B is one, not a lot of books, but one very, very long book. We want to preprocess B such that if you show me any word in the book, if you ask me, is the word W, hello, appears anywhere in the book, here is my book, you will ask is ABA appeared anywhere in the book, then I can answer quickly, yes, it appears, because how do I build the book? W will be in the book, ABA will be in the book, if and only if W is a prefix or some suffix of the book. So I take all the suffixes of the book will be only the last letter, or the last two letters, or the last three letters, the last four, the last five. These will be all my suffixes, created a try for them. And now I'm asking, is ABA is a prefix of any of these suffixes? And indeed you see that ABA appears as a prefix of the suffix ABAB. So what will be the time after building the try? If I have a word W and the length of W is K, how much time will it take you to find W in this book? After building the suffix try, of course. Or how we are performing a find operation. Where I perform a find operation in the suffix tree. And what is the time to perform a find operation in a try? The suffix tree is nothing but a try, but the try has a special structure. They're all prefixes of something. How much time does it take to perform find, or to perform delete, or to perform insert into the try? I don't care how many words there are. I don't care how many characters there are. I only care how many characters there are in W itself. So performing find, but discovering that W is indeed a prefix of one of these suffixes, will take order of K. You start from the root and you follow the letters of W, like A, B, A. Then in the tree, I took all my suffixes, insert them into the try, started from an empty try and insert all of them. So this path, for example, will correspond to B, A, B, A. And if I am performing find of ABA, ABA is not a word in my dictionary, it's not a word in S, but it is a prefix of a word in my dictionary. Right? If I look for ABA and asking, is ABA a prefix of one of these suffixes, then let's try. How do I perform find? Going to the root, look at the first letter of my query. That is. Right now I'm concentrating on the A right here. If A leads to null, I can say this string is not in the book, but the A character from the root is pointing to a real node, so I'll go to this node. Now I'm following the B. The B will take me over here. I'll follow the A once again, the last character, reach to this node, and since there are nodes underneath it, it means that ABA is actually a prefix of one of these suffixes, so I'm sure that actually ABA appears somewhere in the book. Again, it's just a result of this lemma, this little claim that we had in the previous slide. I went back one slide. That says W appears somewhere in the book, if and only if W, I will enjoy saying this sentence, W is a prefix of a suffix of this book. Now, as we discussed yesterday, the problem with this book is that the memory, and I let you in homework 6 play with this more, that the memory is order of n squared, because that's the total length of all the suffixes. This is a book where n is a number of characters in the book, in B. If my book has 1 kilobyte length, then I need 1 megabyte to store it. If my book is 1 megabyte, then I need 1 terabyte to store the whole book. Way too much. So our algorithm says, create a book and bite the bullet. Stay with so much memory. It's actually theta. It's both order of n squared and omega of n squared in the worst case. Bite the bullet temporarily. I spend n squared time, but for a bit. And remember, I'm building this data structure not to use it once for one query. If I just want to know if a word, ABA, appeared in the book, and that's my whole task, I'll just go linearly in the book and just do a search for ABA in this whole book once. I don't need the whole try. Don't need this gymnastic. I'm building the book because I'm planning to use it for many queries. I'm building data structure to help, say, search in Wikipedia. I'm taking the whole Wikipedia and I'm building this data structure to look for strings in the whole Wikipedia. And this data structure is going to be used for many strings, many queries. And I cannot spend this memory all the time. There are other books that I need to process. There will be other books that I need to process. So now I'm going, after building my big book and spending the n squared time, I'm going to compress the suffix tree. I'm going to compress the suffix tree. And pay attention, it's one of the gems, I think, of the algorithm course. It's really nice use of theory. So here I'll use the word to be consistent with literature. I'll use the word thread to denote what I call the path. A few slides ago, it will be any sequence of nodes starting at U and ending at V in the try, in the suffix tree, in the try, with the property that each one of them has only one child. A thread is a sequence of nodes with the property that any of them, excluding the last one, any of them, excluding the last one, has only one child. The last one might have 0 children, the last one might have 2 children, I don't care. But a thread is defined as such a sequence of nodes, each one has only one child. Now, we had the idea of path compression. The idea of path compression for tries said I have a sequence of nodes, each one has only one child. We just mentioned it. It has only one child. It doesn't need to be the same letter. It could be different letter, whatever, but I'm just looking at this string and I'll store the strings that it represents specifically in the node itself. This is very similar to the ideas that I'm going to describe. Every time that I'm going to see a shred, the shred is just a run in the suffix tree, I'm going to compress it into one node. And this one node, supposedly, in just normal try, this one node has to store the actual string that is associated with it. And the string might be very long. So I still save some space. Why am I still saving some space? Because I'm wasting a lot of empty space in each one of these nodes, a lot of cells without a pointer, But that is my only save up so far, if I just use the old technique of compression. But in the context of suffix tree, I enjoy something that I didn't have in just normal twice. What is a new thing that happened in suffix tree? Look at this. Look at the string that it corresponds to. The string that it corresponds to, as long as all the nodes here don't have a flag that something ends in them, let's assume that no word ends in any of these nodes. Remember, if a word ends, then you are putting a flag of 1. Let's assume that the flag is 0 for all these nodes. So describe the idea. I'll tell you later how it works differently. But at the moment, I assume that all these nodes, excluding maybe the last one, has a flag of 0. That is, no suffix ends there. So how could I create this part? Well, sometimes I inserted one of these suffixes, one of the string, and to insert it, I had to create a lot of nodes, and each one of them, even after I'm done with all the insertion, each one of them only have one child. So it corresponds to a string. You know it already for any compressed tree. But here is a new idea. I'm going to store the book somewhere. If I'm going to build a search engine for Wikipedia, I'm going to store the text of Wikipedia somewhere. You have in your memory the text of Wikipedia. You have in your memory the whole book. Well, where did these strings come from? It created when I inserted one of the suffixes. So it is string that appears somewhere in the book. So no matter what the length of the string, to know what is the string, all I need to ask is where does the string start in the book and where does it end in the book. I just need 2 numbers. I need to say instead of this long string of instead of the string that described here of A, D, B, etc., A, D, B, D, that I'm presenting here. All I'm going to store when I'm compressing the tree is go to the book and take the string that starts at index 7, the A, and the string ends at index 10, the D. It must appear somewhere in the book. I know it when I created this string. When I created this shred, when I performed the insert. Make sense? So now I got this node that I created in the try, in the compressed try, in the compressed path, compressed shreds, doesn't need to store this long string. The string is somewhere in the book. All it needs to ask is where in the book this string appears, where is this ending. And I don't need to search for it because I know when I created this thread what was the suffix that I was in the business of inserting. So I know exactly where it started and when it ends. Cool? So after the compiler, so now every node has only a constant memory. Assuming that the alphabet is constant, of course, only 4 letters, only 256 letters. Assuming that the alphabet is constant, now each node only takes a constant memory. And it's only now with this compression. Because when I'm compressing a node in the previous try, if I need inside this node to write A, B, C, A, B, C, B, C, A, B, C, dot, 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 dot. If I need to store inside the node a very long string, then I have no clue how much memory I'm spending on this node. Now finally I have knowledge that no matter how long the string that you represent is, it still appears in the book, so you just need the 2 pointers to indices in the book and stored it in this node, and voila, you're off to go. At least this node needs constant memory. Now, there are other nodes, of course, the traditional nodes that we started with the twice, but they, of course, take constant memory as well. They don't store strings in them. Okay, and the big question that comes now is, sure, you save memory by some amount, so, but remember, we needed, when we started with the try, we needed n squared memory, and the number of characters in the book. When I build the suffix tree, at the beginning I needed quadratic memory. I performed this diet. I compressed all these threads. So now I'm down to less memory, but what can I say about how much memory right now? 30 seconds. Anybody can say something about the new memory? About the memory requirement right now? Now I'm sure that every node needs a constant memory. How much memory do I need right now? Can you prove anything?
This is just an idea, but is it like n over the number of words? Like n over w, because we only like store the threads?
Well, I stored all the suffixes, so when I started from this point, my tree could have this quadratic memory, because what is the total, if I have n words, n letters in my book, then my suffixes are of length 5 plus 4 plus 3 plus 2 plus 1. That is 1 plus 2 plus 3 plus this, you know, our beloved 1 plus 2. All the way up to n, that was the total length of all the suffixes when I started with. And so that's where the n square appeared from. But now I compressed something. So can I say something about how many nodes do I have in this new tree? Before the diet, this tree, before the compression, this tree might have n square many nodes.
Factorial.
Ooh, no. N factorial? No. I mean, the worst was to just perform, before the compression, I just created a try that contains all the suffixes of the book, just as normal book, just as normal try. In every try, the number, maybe I didn't say it yesterday, in every try, if you have the word W1, W2, WK, these are the words that I'm inserting into the try, then an upper bound on the number of nodes in the try that I built for this word. Remember that's a correct spelling. Try will be sigma of the length of WI. That is how many letters you have in the first word plus how many letters you have in the second word. Why? Because when I'm inserting a new word into the try, think about it, just a normal try like this. When I'm inserting a new word, how many new nodes do I have to generate? At most one per each letter of the new word. There could be some recycling, so it's only an upper bound. Some of these nodes might be recycled, but altogether you're paying the total length that goes from 1 to k of all the words that you used so far. So that's where the n square can come from. But of course, even in a try, there could be, the root is going to be used for many words. The children of the root are going to use for many words. So one node might appear in several words, but all in all, that's actually a bound, constant times this number will bound, and actually I'm asking to prove it in homework 6, to say that will be the memory. But now I did the compression in this way. And I ask how many nodes will I have in the new try. So the algorithm so far will be takes the book, create all the suffixes of this book, insert them into start from create an empty try, insert all the suffixes into this try. And you might need n-square memory. A search will still takes order W, but the memory is horrendous. What happened after I got rid of all these threads, all these ones? Now I'm in the case that every node has at least 2 children. But if it has only one child, I compress it with its parent and grandparent and grandparents. If I have a sequence of nodes that has only one child, anywhere in the tree, there might be a lot of such sequences, there might be a lot of threads. But every such thread I fully compressed. So in my new tree, after this compression, every node will have at least 2 children, maybe more, or it is a leaf and then it doesn't have children. So what did I create so far? I created a blessed tree, a tree that every internal node has at least 2 children. Agree? Zoom? After the compression, every node will have either, it will have either no children, where it's a leaf, or has at least 2 children. Because if it had 1, then I took it plus its children and compress them into one compressed node. The new tree is more or less a blessed tree, what we started our meeting today with. And I'll get back to why it's only more or less and not exactly. Out of this compression, because if every node that has only one child got squished together with its children into a single node. And the single node, as opposed to normal try, the single node still needs only constant memory. So the number of internal nodes after the compression in a blessed tree is small or equal than the number of leaves, actually the number of leaves minus 1. That was the lemma that we proved by induction. That's why I showed you this lemma. Now, every leaf, what side should I stand? Every leaf is the last letter of a suffix, of the suffix of B. How did I get to this leaf? I inserted a suffix, and this leaf was just the last letter of the suffix. And the last letter of the suffix is just the last letter of the book. How many different suffixes do you have? Number of suffixes is n. Maybe n plus 1 if you count the empty suffix. So the number of leaves is n. Our lemma told us that the number of internal nodes is n as well. And every node needs only constant memory, so the total amount of memory that I need for the whole creature is only linear altogether. I don't know what's your opinion. I think that it's extremely cool. Okay. So once again, let's go over this argument. The number of leaves, how do I generate a leaf of the suffix tree? The leaf was created when I inserted a suffix, one of the n suffixes, and that was just the last letter of the suffix. So the total number of leaves will be at most n. And I need to tell you why it's at most, but not exactly. But at the moment, the number of leaves is at most n. You cannot create a leaf without a suffix that just ends either. The suffix is the whole thing that let's remind everybody what is a suffix. The suffix is what you're getting from the book when you deleted some characters at the beginning, but then you're taking everything after these characters that you ended, all the way until the end of the book. So there are only n leaves. After the compression, every internal node has at least 2 children. That's what blessed tree is. You have leaves with no children, and every internal node, everything that is not a leaf has at least 2 children. We have a lemma that says what is the relationship between the number of nodes and the number of internal nodes versus the number of leaves in such a tree. It's what we call the blessed tree, and in such a tree, the lemma said that the number of internal nodes is smaller than the number of leaves. But the number of leaves is the number of suffixes, which is n. It's most the number of suffixes, which is n. So altogether, I needed n. I'll get to this slide in a sec. Altogether, so far, the total number of nodes. So now each node needs order of 1 memory. Every internal node needs a constant memory. Number of internal nodes is small or equal because of the lemma, the blessed lemma. The blessed lemma said that the number of internal nodes is smaller than the number of leaves, -1 actually, which in turn is small or equal than the number of suffixes, small or equal than the number of suffixes, which is n. So altogether, how much memory do I need? I need n nodes for leaves plus n nodes for internal, and each node needs a constant memory, so altogether it's order n memory, linear memory. That is, if you're holding the book, you're already spending n memory, so you might need to double, enlarge it by a constant, but that's all you need. Still, it's linear, it's not quadratic. Instead of if your book is 1 megabyte, then you're moving to maybe 5 megabytes, but not to 1 terabyte.
Sorry, just a quick clarification.
Sure.
Is it number of leaves or number of leaves minus 1 in that like inequality up there?
Minus 1. But it's still small or equal for the reasons that I'll show in a second. With the number of leaves minus 1, yes.
Okay,
Coming from the level. So all in all, I'm down to linear memory that I can reasonably, if I can hold the book, then I reasonably can hold this data structure. Now I can answer queries in search times that is proportional only to not the whole Wikipedia. You're searching for alone, you'll find alone alone has 4 letters, in order of 4, you'll find it. So where am I lying in all this discussion? I said that a shred corresponds to a set of nodes. Each one has 1 child, and all of them has a flag being 0, except for the last one. Let's remember what is this flag. Let's assume that our book, it's time. Let's assume that my book is the letter A, B, A. Here is my book. Let's create a suffix tree for this book. My alphabet, sigma, my alphabet contains only the letters A and B. Not a lot of letters in my alphabet. So my first suffix is just A. Let's insert it. I created a node for it. That's a root. And remember, the node has a flag that tells me if a word in my set ends here or not. The empty suffix, yes, the flag is 1. There is just because of the empty suffix. Now, there are 2 pointers, one for the A side, one for the B side. I'm inserting only A. So that is my new tree after inserting only A. Let's write the flag as in red. So one that will end here when I'll insert just the empty one, one's end here. Next I'm inserting A, the next suffix. So A, and from the A part over here, I'm generating another one of this node. By the way, notice that on this node, by the way, I can also write where this A came from. Right? I know what I'm inserted. I'm inserting the string that is just ending at 5 and starting at index 1, 2, 3, 4, 5. So I'll write here that it starts at index 5, but it also ends at index 5. That's when I'm searching for A, I can find this suffix where the suffix appears at index 5. It tells me not that it appears, or not only that it appears in Wikipedia, but also where is this appearing. Take the cursor, if we are talking about editor, take the cursor exactly to the right place. Now I'm inserting the string AA. So inserting AA, writing this as 1, and at which index AA appear, or where, at least where does it start? At index 4. Next, I'm inserting, let's use blue green to denote what I'm inserting. I'm inserting AAA. How do I do it? How is the insert algorithm works? I'm performing first find of AAA. Find of AAA goes to the root. Is there a pointer leading from this root at cell A? Yes, go to this node. Follow the A, follow the A. Is there a pointer leading from this node? Now I'm about the last A. Is there a pointer that's leading from this guy? No, so create a new node and insert it. And this will be A, B, as before, that points to null. The flag is 1 because AAA is a word in the alphabet. And I'll say that, by the way, it appears in the book in index 3. Now I'll insert BAAA just for completeness. So it's B, A, 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 A. And I'll write this node, somebody ends here, so I'll write it's 1. And the index that I'm writing actually for all the nodes along this shred, what index, what auxiliary data. So the flag for all these nodes is 0. Right, because so far no words ended there. The flag is 0, but what is the index that I write to all of them? Well, I know where this character came from, so I'll insert, so I'll change it to, I'll write next to it, that it all came from index 2. Everybody with me? So in this way, now if I'm looking for the word perform find of BA, BA appeared somewhere in the book, and I can find it by just follow the tree, and I'll get to this node that will tell me, yes, the word BA appears somewhere in the book in index 2. Now I'm inserting, finally, the last guy, AB, AAA. So what happened here? I'm going to insert A, B, A, B, and now there will be a shred of words over here. A, B, A, A, A. And I need to figure out the other details. But why does it disturb me with my lemma? Because let's look at this shred, for example. Look at this shred that consists of only these two guys. You have a node here that has its flag on, and there is index associated with this that might be different than the index of the last node. They came from different prefixes. This node came from different prefixes of this node. So when I'm doing the compression, I'm actually careful not to have in the path, you have to stop the compression the moment that you're getting to a node with index 1. In particular, there will be nothing that I can compress here. Again, if you have, I'll be done in 30 seconds. If I have a here is a shred as before. It read as before, but this node has a flag equal 1. There was a prefix that ended here. And there is also a prefix that ended here. So this is 1, 0, 0, 100. There is a little technicality here that says you can only compress things only if no word ended itself. So my new compression will be something like this will be one new node, one compressed node, and this will be one compressed node. Otherwise, you're losing the information about this one. So there will be altogether these special nodes that are internal, but you cannot make them part of the path. So the actual number of nodes is not 2n, but it's actually 3n when we are doing it, because the number of these special nodes where a suffix ended in them, well, we know how many suffixes are ending, how many suffixes we have, only n. So the number of special nodes is also n. Altogether 3n, it's actually back to 2n if you are looking more carefully. Either way, we are back to linear memory, voila. So that's what I needed to show you about suffix trees. Remember, big data structure, but you can now work on it. And you can also do this incremental search, like as we discussed. You go to Chrome, you start typing www, and it ends, of course, the most likely place that you're always visiting, www.cs.arizona.edu, or whatever. Whatever it thinks that is the most likely that fits the prefix. How does it know to what is a prefix that most makes sense? Because at some point you inserted the old path of www.arizona.edu, it's a long path, but in particular you will write something at the node and let you figure it out. In the homework, that if I just type now, I start a new search, or you just type www, and somehow this node will know what is the most likely suffix that does the auto-completion. What is a word that is the most likely, the ending out of all these words, what is the most likely ending, a prefix, a suffix to the prefix that I just typed. I typed www, that's my prefix, and the auto-completion is nothing but guessing what is the most likely suffix out of all the addresses that you ever typed. Good. Questions? Thanks. Sorry for staying extra time. Next, we are going to speak about union find, and of course, any questions from the homeworks that you are curious about seeing their solutions. Any discussions about anything, mostly homework solutions that you want to see, solutions to homework questions and or practice questions or anything else. As usual, I'll add more practice questions to homework 6. And you came late, so you didn't hear what I said originally, that I really recommend submitting homework 6, even if it will not improve your grade. And the reason that I suggest to, it's not, I mean, I take only the 5 highest homeworks grades. But out of the 6 homeworks, I'm using only the 5 best ones. Nevertheless, if I have one student that got 70. I have one student that got 70 in homework, what is this? Homework 1, homework 2, homework 5, and did not submit homework 6. And another student that got but did submit homework 6. To the average, it will not make a difference. But in my book, the second student is trying much harder to work on it, takes the course more seriously, spends the extra time and the extra effort to check it. And it's also good preparation for the midterm, of course, but also submitting homework 6, like, reasonably. Don't submit it 3-0, but even if it's slower, it could be, even if it's slower, still I'll it gets bonus points on my book as class participation. You're trying harder to take the course more seriously or investing the time. Okay, thanks everybody.